Welcome to July's Leetcode challenge. Today's problem is kth smallest element in a sorted matrix. Given an m times n matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. Now note that it is the kth smallest element in the sorted order, not the kth distinct element. So if we had duplicates, we're still looking at the index number, not the distinct element. Okay, so at first glance, it kind of looks like this is just sorted in like row to column fashion, 1, 5, 9, 10, 11, 13. So why don't we use like divisors and modulars? But that's not going to work because you can easily imagine some examples where we're sorted row and column, but it's not going to be sorted in that same direction. So this technically is sorted row and column, but if we moved left to right here, that wouldn't work because it's not in sorted order. So that's not going to work. Is there anything we could take advantage of given that it's sorted? Well, before we do that, why don't we just do a brute force method? Let's just flatten this matrix into a 1D array and see if we could sort it and return the kth element in there. And all we have to do then is say for L in matrix. We'll just extend our temporary array with the list and make sure to sort this and literally just return the temp k minus 1 element. Right, so this would be the brute force method, and it actually does work. In fact, it gets accepted here because time complexity wise, it's going to be what? N squared to the log of n squared because of this sort here. So, at first glance, I thought like, okay, well, this is it. Maybe that's it. That's the solution. But something didn't sit right with me because I knew that because it's sorted in row and column fashion, there has to be something we can take advantage of here. Otherwise, it's like we're literally just sorting the whole thing. We're not taking advantage of the fact that it's sorted in row and column. So one way that you could do that is to do a binary search, but instead of looking at the elements here, what we're going to do is look at the gap between the minimum number and the maximum number. That's going to be our range where we do a binary search. And we're going to do another binary search through each row to find how many elements are less than the element that we're searching for. And as soon as we find our left and right range equal one another and our k is equal to 8, then we can return whatever number we come up with. So one of the few things we do know about this matrix is that the top left right here and the bottom right is going to be the min and max of our matrix, right? So let's first take advantage of that. We'll set our left and right pointers as well as the n here. The left pointer is going to be matrix of 0, 0. Right pointer is going to be matrix of -1, -1. And the n is just going to be what? Length of matrix. So first, let's write a helper method to show us how many elements are less than whatever input that we put in to check whether we should move our left pointer to the middle or the right pointer to the middle. So we'll call this less than k, and we'll pass in some number. So let's see. We're going to count the numbers, initialize it with 0, and we'll say for, say, row in range of n. Let's do a binary search here. We'll do a bisect, but we have to do a bisect right. And the reason for that is, let's see here. The reason for that is if we find a number that's like equal to all these numbers here, we want to go all the way to the right side to see how many are less than k. So we'll say bisect right, and then we'll add this number to our count here. Let's go x. Finally, return our count. And now let's do our binary search. So while L is less than R, calculate the mid, which is going to be L plus R divided by 2. If less than k, less k of mid, if this value is less than k, then we want to move our left pointer to the middle, right? And we're going to have to add 1 here because we want to find the right gap here. So otherwise, we say R equals to mid. And then we can just return our L or R. Doesn't matter which one. So let's see if this works. Okay, that does look like it's working, so submit it. And there you go. So that's accepted as well. Time complexity wise, this would be, I think it's going to be log, it's going to be n to the log of whatever the gap between the min and max is. So we'll call that m, so n log of a right here. I believe that's correct. Although this part here might make it n log n. N log n times log of the m. Something like that. But either way, when I look at the speed, it's about the same because of our constraints. It really depends on what would be our constraints. If we had like really large n's, this solution would be much better. Otherwise, the brute force method works fine, and it's in fact sometimes faster when we run it and look at the time. So it's up to you. I did see one other solution that is O of n time, but it was so complicated. It used math and median values, and it was just way too complex for me to go through. So we'll just end it here. Thanks for watching my channel. And remember, do not trust me. I know nothing.